Hello, everyone. Today's topic is interest rate derivative valuation. We will focus on linear derivatives in this session. There will be a follow-up session on non-linear derivatives. So when we say linear interest rate derivatives, typically we are referring to simple bonds, right? Zero coupon bonds, fixed coupon bonds, floating coupon bonds, forward rate agreements, and interest rate swaps. And when we talk about nonlinear derivatives, obviously it will include options. So that will be the next class, where we'll discuss about call options and put options on bonds, caplets, floatlets, caps, floors, swaptions. All right. Just a quick audio check. You guys can still hear me, right? Okay. Maybe there is something wrong with your audio, Pujita. Okay. So that being said, why today's class is special is because it is multifaceted. All right. What we are going to do is learn how to value derivatives, interest rate derivatives, but not in a way that we are taught in schools. Typically in academic exercise, we are given the set of static inputs, right? And then we calculate the value of a derivative. That's it. You are not worried about what happens tomorrow. Tomorrow or after one quarter, let's say, things change. The time itself changes, the valuation date changes, and the underlying risk factors change. So it is not enough to learn how to value a derivative on the spot, right, at the moment, but we also need to learn how do we get the estimate of values in future. So I call that dynamic valuation of derivatives. So you need to have an idea of how the risk factors evolve, and how the time obviously moves forward, right? Everybody knows how the time moves. There is no doubt about it. You know exactly what date it will be after one quarter. But in terms of risk factor movement, we have opinions. We have views or we have scenarios. You can do a simulation. Okay. So long story short, we are trying to learn how do we value derivative dynamically, okay, when the underlying risk factors and the time changes. Now, what is the use of that? Why do we need to know that? I'll give you two prime use cases. One is, let's say you're trying to evaluate dynamic balance sheet, which is the integral part of ICAP, ILAP. So you're trying to do projection, quarterly projections, and you want to see under each scenario of the balance sheet going forward, how does your derivative portfolio look like? Okay. Because it has implications in terms of overall value. If there is loss in your MTM, then there will be an outflow in your collateral, and there are cash flow impacts, right? So in terms of dynamic balance sheet, you definitely want to evaluate derivatives several quarters ahead going forward. And the second important other use case would be if you know about counterparty credit risk. If you are aware of exposure metrics, some of you may be aware, some of you may not be aware. So in counterparty credit risk, we need to draw exposure profiles of derivatives. And that becomes an input to a lot of these different calculations. Okay, so if you have heard of PFE or expected exposure or even CVA calculation, we need to come up with a distribution of derivative values at different points in time in future. Okay, so that's based on simulation. So yeah, given this context, today's topic is focused on valuation of derivatives dynamically when the underlying risk factors and the time evolves. Okay, so it can be used in a lot of different applications. We'll focus on interest rate derivatives, linear derivatives, as I mentioned, okay, in this session. All right, so with that being said, let's proceed. So today we'll cover all of these. I'm pretty sure all of you have some idea of, interest rates, spot rates, forward rates, but I will introduce everything to you from scratch. because I see a lot of the times they don't do justice to these definitions properly. You do need diagrams, and you need proper analogy and explanation to understand these things clearly. Just this alone, particular object, interest rate, is not explained properly in a lot of the academic books. So we'll start from there and cover all of these things. All right. If you have any questions, let me put in the chat box. We can discuss. Okay. First and foremost, what is a rate or interest rate for that matter? When we look at interest rate, there are three time instances involved. Okay. Small t, I'm calling small t, capital T1, capital T2. You can see in the picture, and obviously they have a relationship. The relationship is small t must be less than equal to capital T1 must be less than T2. That is the relationship they have to follow. Obviously, the time instances have to be real numbers. They cannot be complex. Okay. All right. So what are these quantities? Small t is the observation date. This is when you observe a particular rate. Okay. Small t is the observation date, which will eventually evolve, because today you are looking at a rate, and then tomorrow you'll be looking at the same rate, but the small t would have moved up by 1 day. Okay, small t keeps evolving, observation date keeps evolving. And then for a rate, uh, predominantly the rate, what does our interest rate mean? Interest rate means at what rate you can grow your money over a period. Okay, so the second aspect is the period. So the period has these two endpoints. So there is a start date of the period T1 and the end date of a period T2. So we're talking about a rate at which you can grow your money. When I say grow your money, you can think of borrowing or lending activity. We're talking on interest rate that is applicable over a period. Start date T1, end date T2. T1, T2 will be, in general, they can be in future. Okay, in general, they can be in future. The period itself can be in a future. And when are you observing that rate? When is that rate available for you to trade in? That is the observation date, small t. So 3 time instances, keep that in mind. Okay. Yeah, these are all the things we discussed. Now let's look at one simple analogy to really drive home this concept. First, let's talk about forward rate. So what is a forward rate? You'll get a forward rate when this condition is satisfied, which means the start of the period for which the rate applies is after t, small time t. Okay, so T1, capital T1 is after the observation date. If that's the case, then we call that rate a forward rate. Now, just to think of an analogy, right? How this is, you can easily understand this. Think of, you're trying to book a hotel in advance. All right, suppose for the new year that's coming, you're trying to book a hotel for 2 nights starting from December 31st, which in our case would be T1, the starting period of your holidays. Okay. Until 2nd of January 2025, which is capital T2. So 2 nights. You're trying to book a hotel for 2 nights. That period is for 2 nights, which is in future, because today is October 20 or something. And you're trying to book that hotel on October. That is small t, which is today. Period is in future. Okay. Now you go to any website, Make My Trip or booking.com, wherever. If you're trying to book the hotel today for the 2 nights in future, you will have some rate, right? Let's say the rate that you observe today on the website is $200 per night. Per night, that is important. $200 per night. So your overall cost would be $400 because it's 2 nights. Interest rates work in exactly similar way. So this is a forward rate, because the period for which the rate applies is in future and you're trying to book in advance. Okay. Everything is similar. Okay. You got the idea of small t, capital T1, capital T2. right? And also to draw the parallel with respect to rate, the rates of hotels are quoted as dollar amount per night, and then you aggregate based on how many days you. Similarly, interest rates are quoted per annum basis. You need a standardized period, right? Per year, how much is the interest, or per 6 months? Nobody use the only one single standard convention for interest rate is per annum. Everything is quoted in per annum basis. Okay, so ultimately, how long your period would be in terms of years and what is the rate per annum, those two will work together to give you the interest amount or interest payment. Okay, so did you understand forward rate and the context that I'm giving? Any questions so far? I asked two different questions. So one probably has a answer yes and the other one no. So let me rephrase again. Do you have any questions? All clear, guys? So far? So far, so good? Yes, FX forward is a little different. We'll cover that later. Maybe in the third class. Third class would be on equities and FX. I hope two classes would be enough to give you all the background material for valuation for interest rate derivatives. Okay, perfect. Now, let's bring T2 close to T1. So let's bring this guy close to T1. So it's just next to T1. Okay, think of this as T2 is 1 instant later than T1. Okay. So in terms of hotel checking analogy, think of getting into the hotel and coming out in 1 instant. Not even staying. It's not even 1 minute, just one instant. Okay. The key word that we use is infinitesimal period. So if you bring T2 very, 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 very close to T1, the period becomes 1 instant. The other word is infinitesimal. Infinitesimal means extremely close to zero. Positive, but still, close to zero. Then we will call this rate as instantaneous forward rate because it is a forward rate that is applicable for 1 instant. So instantaneous forward rate. When you say instantaneous forward rate, you don't need three time parameters. You only need two because you know observation date is small t, start date has collapsed. Start date, let's call start date as t. Instead of T1, I'm calling that T. And the end date is right next to T. So T plus, I don't know, delta, maybe. So, right, we all know that this is 1 instant, right? So we don't need a third time parameter. We can just simply use these two. Okay, so we denote instantaneous forward rate as F, small f, T comma, capital T. This, everybody understands this. This means it is available at small t, applicable from capital T to the next instant. So you don't need three type parameters, just two is fine. So that is instantaneous forward rate. Okay. Now this is important from a modeling perspective, and this is something we'll look at in the next class. Today, we don't need this. Okay, next, coming to spot rate. So we talked about forward rate. Now we're going to talk about spot rate. Spot means right away. Okay, when we say on the spot, what does that mean? Right away. You are not, there is no waiting time or nothing is happening in advance. Spot means right away. So spot rate would mean something similar. Spot rate means your starting period, capital T1, coincides with the observation date. That means it's a rate that starts right away. Whenever you are observing the rate, the start of the investment period or the rate period is that date because it's on the spot, right? So it's called spot rate and it is characterized by two time instances. You don't need three because there is nothing forward happening, right? So T is equal to capital T1 and we don't need T2. We can just call it as capital T. So why call T1, T2? We only need two time instances. All right. So this is called as a spot rate, where the starting of the rate period coincides with the observation date. They are the same. I will denote it as RTT. Okay. So forward rate notation is this. Instantaneous forward is this. And spot rate I'll denote as RTT. This is not instantaneous, mind you. Okay. This is simply saying that the first two time coordinates are the same. So you don't need to separate them. Again, on this guy, if I try to bring T2 close to T1, so T2 is one instant after T1, then it's called as, obviously it'll become instantaneous spot rate. That means your rate is starting right away, but the period for which it is applicable is just one instant. Instantaneous spot rate. The other popular word for this is short rate. So all these short rate models that you have heard, right? Maybe you heard, maybe you didn't. A Vasicek model, CIR, Holy, Hull and White. There are a plethora of short rate models. They are popular. They are fast, um, right? So short rate essentially means this. Okay, instantaneous spot rate. And the spot rate itself had only two time instances. And when you bring capital T close to T, essentially you only need one time instance T. And we denote it as R, small r in the bracket T. This is the notation. Pretty much every book uses this notation for short rate. It is RT. This encompasses three time instances inside itself. Starts at T, sorry, observed at T, starts at T, ends after one time instant. So you only need T. Okay, spot rate, I hope you understood. Let's proceed. The next idea is year fraction. So remember what I said, all interest rates are quoted in per annum basis. Now, obviously, your length of period would be different. Sometimes you're talking about 6 months, 1 year, 2 years, quarter, even sometimes overnight, right? So when your period length of period is dynamic, you need a measure to find the time period in terms of years. Between any two time instances, I need to find out the distance between these two instances in terms of years. Why? Because your rate is per year. Your rate is per year. Think of a car. You're driving a car, and the speed is always miles per hour here in US. In everywhere else, kilometer per hour. Per hour, right? Your speedometer gives you a rate that is per hour. So naturally, if somebody asks you how much distance you traveled, you need only one input, which is how many hours did you drive? Assuming speed is constant. And then multiply hours with the rate, which is kilometer per hour, you get kilometers. Exactly same idea. How much interest payment you will get over this period? Well, the rate is per year. And then you do a times number of years. So you'll get the overall interest payment in dollar amount. Same idea. So we need a measure to figure out the distance between two time instances. Okay. That's called as year fraction. The notation I will be using is tau t comma t, which basically means what's the time distance between these two instances in terms of years. Okay, so let's say there are two dates, D1 and D2. D1 will have some day, day and month and year, correct? Just two dates. These are three things you need to define a date. Day, which month, which year. To figure out the time distance between D1 and D2, we need some convention. So there are three popular conventions. There are many more also. And based on the convention that you use, your year fraction would be different. How many years are contained within that period? That's what we're trying to figure out. Okay. The first convention is actual by 365. If you're going by this convention, the formula to calculate year fraction between these two dates is simply d2 minus d1 divided by 365. Number of days between these two divided by 365. That's the formula. One thing I have not given here is handling of holidays. It becomes really complicated. So I conveniently escaped those calculations. But there will be treatment of holidays, which will be a separate module in your software that you have to define how you want to treat holidays. Do you want to count them? Do you want to skip them? Or there are many different rules. So based on that, your answer might change a little bit. The second convention is act by 360. Okay, so basically you assume that a year has 360 days. The year fraction would be difference in the dates in days divided by 360. We also have a 30 by 360 kind day count convention. These are called as day count convention. And looks like a complicated formula, but it's not complicated. It's just max, min, these guys are there. So you can use this to calculate year fraction based on 30 by 360 day count convention. Question from Gaurang, what is followed in industry? There is no standard rule. Different say treasury uses act by 365 convention. Municipal bonds follow another convention. Corporate bonds might follow something else. So it's all over the place. All three are used. All three are popular. Okay, perfect. Let me know if you have any questions. Okay, still on the building blocks of interest rates. The next idea is compounding frequency. That is also a key ingredient that you need to calculate interest amount that is applicable for a period. Compounding frequency basically means how many times within that period you want to compound. Okay, so let's say we have simple compounding where there is no compounding, just linearly grow at the rate given to you. Linear, right? And let's say I want to compound it twice in the period. So what you will do is break it into two parts. Grow your money, whatever you got, and then on top of that, you grow again. Okay, so 2 times compounding. Right? So the second time you earn interest on the interest you earned in the first period. That's the whole idea. All right. Sorry, was there a question? Let me see. For leap years, are there any exceptions to year fraction calculation? No, we use 365 as a standard. But I'm not like 100% sure. So we'll have to probably look at that. But that's a good question. Okay. Maybe if somebody has the answer, he can give. All right. So coming back to compounding, you got the idea of compounding, right? So how many times we want to compound the growth in that period? The starting with not the simple one, but this is academically the most profound, is called continuous compounding. So continuous compounding means you are continuously compounding. Okay. All right. So we're trying to figure out if you invest $1 at the start of the period. If you invest $1 at the start of the period, how much money you'll have at the end of the period? That's what we are trying to figure out. Give me one moment. Okay. So under continuous compounding, I'm calling the rate as RTT. So it will be e to the power, the rate that is applicable. Remember, this rate is always per annum. So you need to multiply the year fraction, which is tau t comma t. Tau t comma t will depend on the convention that you're using. Remember, that's what we talked about for the year fraction. So rate e to the power rate times year fraction. That's how much money you'll have at the end of the period. Okay. Next, simple compounding. So in simple compounding, we are not compounding multiple times, it's just linear growth. Okay. So let's call the rate for simple compounding as L. The money that you'll have at the end of the period is simply 1 plus L times year fraction, linear growth. Okay. If you want to calculate just the interest amount, it will be this amount minus 1, because 1 is your initial investment. These are all your final value of the wealth that you'll get at the end of the period. So if you subtract the initial amount, it will give you the interest that you earned. Question from Rahul, can you please explain year fraction in continuous compounding? Oh, these are separate ideas. See, continuous compounding uh, basically means that you are compounding every second, every instant. Okay. And the rate given to you in terms of continuous compounding is R. Year fraction is separate calculation. What is the distance between the time, what is the length of the period in terms of years? For that, you use these ideas. Okay, based on your convention, you'll get the year fraction. Take that, plug it in here, you'll get the amount you will have at the end of the period using continuous compounding. R is a rate that is quoted in continuous compounding, which means this is the rate at which you grow your money and you compound every instant. Okay. This is how you just quote the rate. So I'll give one example. When you are driving a car, I can quote the speed. Speed is a rate, same idea. Speed in miles per hour or kilometer per hour, different units. Okay. So accordingly, you modify your calculations. All right, simple compounding, you understood, it's just a linear growth. 1 plus, so I'm calling, using the notation L to indicate that it is a simply compounded interest rate. This is R is continuously compounded interest rate. Excuse me. Similarly, you go to annual compounding. So basically you compound after every 1 year. Okay, you break the interval in terms of years. Then at the end of each year, how much money you have, in the next period, you earn interest on top of that. Okay. So in annual compounding, the rate, the notation I'm using is Y for annual compounding. And this is the formula. So this is probably very easy to understand. So in the first year, you will grow your money 0 to, let's say, 1, right? This is how much you'll have at the end of first year based on the rate applicable for the first year, which is from 0 to 1. Second year, you'll earn interest on top of this amount, which you already accumulated. So 1 plus Y starting from first year end to second year. And you keep doing that. Okay. And you have, these are the number of years, right? So let's say there are 3 years. So next one would be Y from 2 to 3. That's it. Now, let's say that the rates are same, flat, for example. Then I can replace it with one quantity and it will be to the power cube, correct? For 3 years. Exactly, that is what is written, to the power year fraction. And you can do even faster compounding, somewhere between, simple compounding to continuous compounding, or yeah, K times per year. So it can be like quarterly compounding or semi-annual compounding. So if it is K times per year, so what you do is break the year into K sub periods and then do the compounding. So for each sub period, your interest rate applicable would be Y divided by K. I'm calling it YK to denote that it is a special type of compounding, which is K times per year. So per year, the rate is YK. So what is the rate per sub period? Because you are dividing the period into K periods. Per period, the rate would be YK divided by K. And the number of periods will become, this is the total year between from here to here, but you have divided the period into K periods. So total number of periods is K times the year fraction. Okay, so you adjust the rate and you adjust the period. That's how you do the compound. Okay, so yeah, today we will use continuous compounding and simple compounding, and you can go back and forth between two different rates. So that's the next topic. How do you convert? How do you perform the conversion between different compounding types? Okay, so somebody has given you that, hey, between these two dates, say say this period is tau. Okay, the year fraction is tau. That's the period. Okay, somebody told you that the continuously compounded rate at which you can grow your money in this period is R. You want to know in what is the equivalent simply compounded rate that will give me the exactly same money. That's what conversion basically means. You're quoting the rate in different compounding frequency. So I know that if it is if the continuous compounding is R, the money that I'll have at the end of the period is e to the power R tau. If I invest $1, of course, it will become this much. An equivalent simply compounded rate BL, which will give me the same money. So that will be how much? Linear growth. These two must be identical. And you go back and forth between, if you're given R, you can find out L. If you are given L, you can find out R. Okay. That is what I've done. E to the power tau 1% tau. If you want to calculate L, it is just e to the power tau minus 1 divided by tau. You can go back and forth. Okay. Different ways of quoting the same kind of growth. Right. All right. Next. How do you go from spot versus spot rate to forward rate? Suppose we want to figure out the forward rate between T1 and T2 standing at time small t. Okay. What is the forward rate applicable between T1 and T2, which is in future? Now that you can calculate that using the two spot rates. The first spot rate, remember, spot rate starts right where you are standing. Okay. The starting period of the spot rate coincides with the observation date. So one spot rate goes from small t to capital T1. That is RTT1. Another spot rate goes from small t to capital T2, which is RTT2. Now, given these two spot rates, the forward rate is kind of sandwiched between these two spot rates. You can calculate or have a relation between these three quantities based on no arbitrage arguments. Okay, it's quite simple, very, very simple. So let's see how we do it. So it's like this. Let me give you a quick analogy. I don't know if that will make sense, but it's something similar. If you're trying to stay in a hotel for 4 nights, right now, starting right away from right now, you are trying to stay in a hotel for 4 nights. So either you can walk into a hotel, just walk in and book it for 4 nights. So you'll get a spot rate. T2 is four actually. T2 is 4 nights. So you get the rate applicable for the entire 4 nights period, but that rate will start is the spot rate because it's your period starts right away. Or you can do one thing. This is a stupid thing to do. You will book there'll be two separate bookings. First, you book for 2 days starting right now. This is 2 days. T1 is 2 days. And then you also change your mind. Do you want to so you go back to your hotel, open the website, and extend your stay by booking in advance for the next 2 days. Everything is done on the same date. Same day transaction. One is spot booking, the duration starts right away, and one is advanced booking, which is the next 2 days. But you're booking 2 tickets. So at the end is the same result, right? You have booked the same hotel for four nights. Okay. In the first one, we're booking for all 4 nights in one shot. In the second one, there are two separate bookings. One is on the spot booking for next 2 days. And then there is another advanced booking which starts from T1 and ends in T2. Okay. So the rates should be such. The rates everywhere, all these three rates should be such that in either case, you should end up paying the same price. Right? Otherwise, there'll be arbitrage. I mean, you would prefer to do one thing versus the other if there is difference in prices. Okay, so same idea. For interest rate, what we need to do is we need to see that at the end of the period T2, you should have exactly the same money. Doesn't matter which way you go. Okay, this way or the second way. So let's do this. If you book using the spot rate that is applicable for the entire time period from small t to T2, then you'll get this rate. So the money that you will grow is using continuous compounding because R is for continuous compounding. E to the power R T2, see the spot rate, which is applicable for the entire period. And the year fraction would be from small t to capital T2. This is the money that you will have at the end of the period. If you book at the spot rate for the entire period, T to capital T2, which should be same as you break it down, book with the spot rate till T1. So the year fraction will be from T to T1. And again, whatever amount you had, you grow it again using the forward rate e to the power f t T1, T2. So the forward rate is applicable between T1 and T2 and the corresponding year fraction between T1 and T2. Both results should match. Otherwise, there will be arbitrage. So from here, I can easily calculate. So e to the power, everything is e to the power, right? So I can just calculate this guy, FTT T1, T2, the forward rate between T1 and T2 as this. Second spot rate times its year fraction minus first spot rate times its year fraction from T divided by the year fraction between T1 and T2. Some of you must have this version maybe you didn't have not seen, but probably you would have seen this. So if we assume small t equal to 0, right? See, in general, I like to keep small t because it is evolving. That's the whole reason. If you're only valuing derivatives for today, right now, you can take small t as 0, no issues. But will be different tomorrow. Okay, so all my valuation formulas will be based on, there will be a valuation date, small t. It can be 0, but in general, you're allowed to change t so that you can see how the value changes. Because tomorrow small t would be different. So if you take small t equal to 0 and the year fraction, you can just simply write probably. So let me rewrite this. R2, okay. T2 minus 0 is T2 minus, let's call this R1 spot rate. And T1 minus 0 is T1 divided by distance between T2 and T1 is just T2 minus T1. This is the version that you probably see popularly in your academic books. But it's a little simplified. This is more general. All right. Okay, the same argument you can do. So we got this answer, which is a continuously compounded forward rate. How do I know it is continuously compounded forward rate? Look at the formula. I have applied it as e to the power rate times year fraction. In this fashion, whenever you apply the growth, it is a continuously compounded rate. So you got the answer in terms of continuously compounded forward rate. If I want to calculate simply compounded forward rate, I'll just use a different formula for growth. Left-hand side remains the same. Spot rate. This is in continuous compounding. This is in continuous compounding. But the second part where I'm growing my money between T1 and T2, the formula that I used, I modified to a linear growth formula, 1 plus a rate times year fraction. So this becomes simply compounded. Simply compounded. And if you simplify, you get, okay. So there is one step involved. Let me quickly do that. So we get FT T1 T2 is equal to, this guy will be come down 1 by tau This will go to the other side. So we have e to the power r t t2 tau t t2 divided by e to the power r t t1 tau t t1 minus 1, correct? This is what I have. But this is 1 by tau, tau as in tau t1 t2. Let me write that. Okay, I'll squeeze it in here. 1 by tau t1 t2. So here's the thing. Oh, we haven't discussed about the bonds yet, right? Okay, we'll park this formula for now. So basically, this 1 divided by e to the power rt t1 times tau t t t1 is the zero coupon bond formula, which matures at t1. And this guy on the numerator, okay, there is a plus. So you take it down, it will become minus, and that is nothing but the zero coupon bond for that matures at t2. So this is another formula. We'll come back to this. Okay. Forward rate, remember, simply compounded forward rate purely given in terms of zero coupon bonds. You don't have to use rates if you don't need to. All right. Let's proceed. Okay. So finally, we have our first instrument, interest rate derivative. When you say bond is a derivative, probably people will scream. They will say bond is not a derivative. But you know, thinking of what is a derivative essentially. Derivative is an instrument which derives its price from the price of an underlier. That's the bookish definition, right? So the value of an instrument that depends on something else, some underlier. So all of these instruments, starting with a zero coupon bond, right? Zero coupon bonds value would depend on interest rate. So technically speaking, it's a derivative of interest rate. Okay, everything is a derivative of interest rate. It is so foundational. Yeah, so we'll keep it to ourselves. So the first instrument that we'll discuss is zero coupon bond, extremely foundational, because the price of the zero coupon bonds are used as discount factors to discount cash flows. So we'll get there. So what is a zero coupon bond? This is the schematic. Your valuation, so small t is always your valuation date. This is where you're standing. There is a zero coupon bond which is maturing at time capital T. The notional or the face value is the $1. Doesn't matter if it is not $1, it's something else, you just scale it up. Okay. All right. So yeah, as I mentioned, it pays $1 at maturity capital T. The valuation of this zero coupon bond is linked to the spot rate that is applicable between T to T. So R, T, T, and vice versa. That means the price depends on spot rate depends on the price. Typically in the market, you see the prices of zero coupon bonds, although they are not that liquid. But let's pretend that there are a lot of zero coupon bonds being traded in the market with different maturities. You can extract the spot rates from those prices. So under continuous compounding, okay, how do you value the zero coupon bond? Simply find the PV, present value, okay? Something that is valued at $1 at time capital T will be how much, what is the value of that at time small t? The notation that I'm using is PTT. Small t is the valuation date. Capital T is the maturity. Okay. If it is under continuous compounded rate, you are given a continuous compounded rate. What will be your discounting? Discounting would be 1 times e to the power minus RTT times year fraction. Okay, so the value of your bond is given by e to the power minus RTT times tau tt. And you can back out the spot rate from the zero coupon bond price, right? So it'll be take log and then log PTT. So e to the e will vanish and then take the one tau tt to the other side as 1 divided by this. So this is how you can extract spot rates from zero coupon bond prices. Any questions so far? But remember, the spot rate that you will get if you use this formula is a continuously compounded spot rate. Continuously compounded spot rate. Are you clear with this? Any questions? You can use simple compounding also. So if you use simple compounding, your valuation would be one. So discounting one back to small t. And this is so whatever you use for compounding as multiplier, you use the same. You divide by the same for discounting, right? Is the simple idea. So discounting would be this 1 plus L times year fraction. Okay, and you can back out the simply compounded spot rate. Just manipulation, right? Take this to this side, 1 by PT minus 1 divided by year fraction. So this formula is to calculate the simply compounded spot rate from the zero coupon bond prices. Okay, I hope this is clear. Uh, Let me know if you have any questions. I'll speed up a little bit. So next concept is zero yield curve and zero bond curve. So what is a zero yield curve? Basically, on any given day, T, observation date, you have an array of bond prices for different maturities. Okay, from all those, so I basically am talking about this PT T1, PT T2. Okay. Yeah, request you to turn off your cameras, please. So keeping small t fixed, you have different maturities, bonds maturing at different maturities. Now, from each of these, you can extract the spot rates. So let's say I'm extracting continuous spot rate. RTT1, I can extract. RTT2, I can extract, right? So for any given day, from the traded bond prices, I can extract the spot rates, which are also called as zero coupon yields. Okay, same thing. And then I'm plotting those here. So this is R, T, T. Right. This is the plot. Typically, this is how this is a utopian or ideal spot rate curve, right? Upward sloping. It conforms to some of the theories that we have, but in real life, it can have any kind of shape. Inverted, U-shaped, first decreasing, then increasing, all kinds of things happen. One key fact here is a caveat. Note that on the x-axis, it is time to maturity. It is not capital T. It is actually T minus T. Time to maturity, because you're standing at, you're creating this yield curve on a particular date, right? For different maturities of the zero coupon bonds, you are extracting the spot rates and plotting them. And what does time to maturity means? T minus T. Okay. Small t, essentially, it becomes like 0. So you will not go wrong by using capital T, but this is just T minus T. Okay. Time to maturity. 2 years, 3 years, 5 months. We are not plotting calendar dates on the x-axis. We're not saying on March 31st, this is the rate. No. Time to maturity, which is in some year fraction. Okay. The reason I like to keep small t here is this is the scene today. Tomorrow, small t gets updated and the yield curve will change. It can become something like this. For the next day, t plus 1, it can look like this. So I'm keeping t as a variable so that, you always at the back of your mind, you think that small t is continuously evolving. Okay. We are moving in time forward. On the right hand side, we have the plot of zero coupon bond prices. Simple. Time to maturity and the prices of the zero coupon bonds. Now, here's the one thing. This curve is a little bit boring because it will always have this shape, downward sloping. Yield curve can have any kind of shape, but this is pretty much always downward sloping because higher maturity zero coupon bonds will trade at a higher discount. So it's always a decreasing function of time to maturity. Okay, so what I'm saying is T1 would be greater than T2 if T2 is greater than T1. All right. Okay. Let's one note here. So you normally have a discrete set of points. Okay. You don't have a continuum of liquid prices. That will never happen. You have maturities at different points, right? 1 month, 2 month, 3 year. So you extract the prices, the spot rates from the liquid zero coupon bond prices. Then you get a discrete set of points, and then you need an interpolation scheme to create a continuous smooth yield curve, because you need to price different derivatives at different maturities. You need the whole curve. Okay, so there are many interpolation schemes. Linear interpolation is there, cubic spline is there, Nelson Siegel is there, very popular. Okay. Yeah, just some more background. So we'll cover this one and then we'll probably take a break. Let's see. So next instrument is simple, fixed coupon bond. So if you look at fixed coupon bond, there is a notional N, which you get at the end of the maturity, capital T. There is two questions. Could you please explain why bond curve is always downward sloping? It's natural, right? Because there is higher discounting. So one zero coupon bond pays $1 here. It has a maturity of, so let's say this is T1. This is 0. This has a maturity of T1. Another zero coupon bond pays $1, has a maturity of T2. Correct. Another zero coupon bond has a maturity T3, pays $1. The price of this guy, you will only discount by this much PV. For this one, you'll discount. There's a much bigger discounting factor because of the time. If you put irresponsible interest rate values, it is possible that for two adjacent points, this relation is not satisfied. But in general, because the further the cash flow in future, the higher will be the discounting factor. Because simply the year fraction is much bigger, right? So naturally, the values will decrease as the time to maturity increases. That's why. And coming to your question, Shiv, I hope I answered your question. Yeah, is this bootstrapping the yield curve? Yes, that is called bootstrapping. Yep. It's a very complicated affair. It's not easy. I mean, if you do it as an academic exercise, it's easy, but there are many different caveats to it. All right, coming to fixed coupon bond. So this is the setup, and we call this a cash flow diagram. All the inflows will be upward facing arrows, and outflows would be downward facing arrows. So let's say we own a fixed coupon bond, we get the face value or notional or principal at the end of the maturity, capital T. Periodically, you get coupon payments. And how the coupon payments are defined is notional times coupon rate, some C, some percentage. And what is the settlement frequency or coupon payment frequency? So let's say every quarter. Then this, remember, all rates are always per annum. So coupon rate 5% is per annum 5%. But then if you are paying it quarterly, okay, then you need to multiply the year fraction for 1 quarter, which is 0.25. So that year fraction I'm taking as tau. Um, so this is the coupon payment you'll get every uh, period. There's a periodic payment. Okay, fixed coupon. Every time this is the constant deterministic value. N is known, tau is known, C is known. At the end also you'll get that coupon and also the notional. Okay. All right. This is fixed rate coupon bond. Now there will be another class on sensitivities. That is also important. Today we'll not bother about sensitivities or duration. Today we'll only talk about valuation. All right. So fixed coupon bond will accept these parameters to give you the value of why I have written it like this is because when you try to code it in any programming language, you need to develop valuation functions that you can call flexibly by passing the input parameters, which will be time elements and contractual elements. So see, this is a time element, calendar date, when is you are trying to value that. This is the schedule, like when are the coupon payments defined in the contract. Notional, again, contractual parameter. Okay. Tau, contractual parameter. What is the settlement or payment frequency? Coupon rate C, contractual parameter. Omega is just the position. If you are long, then +1. If you're short, then -1. Okay. So these are the input parameters that you need. On top of this, you need reference data, which is the yield curve. I did not put it in this function because assuming that you already have bootstrapped the spot rate curve for the time date small t, this is ready with you. So you can price a fixed rate coupon bond, taking the yield curve as the input, which is the market reference data. And all of these are contractual parameters. So you create a valuation function in Python or Java or whatever, and you need to call it to give you the value for a given date. When your yield curve gets updated, you can um, revalue that. Okay. So what is the value? Value is very easy. It's just discounting, right? So basically, you need to look at this picture as an assembly of zero coupon bonds. The only difference is we don't have $1. We have some other dollars, but that's fine. It's just a scaling of zero coupon bonds. Okay. All of these are zero coupon bonds. 1, 2, 3, 4. How many have you? So you see, this is the scaling factor and just sum of zero coupon bonds. Every zero coupon bond being valued at time small t, but have different maturities, TI. Okay. TI goes from, I goes from 1 to N. So this is, you can call this as TN and this as T1, let's say. All right. All the coupons getting discounted by their respective discounting factor, which are the zero coupon bonds with the same maturity. And finally, you also have the notional that you discount from Tn to T, small t. This is the formula for valuation of a fixed coupon bond. Any questions, guys? Clear, everyone? I know some of you probably are thinking this is all kindergarten stuff, easy stuff. Believe me or not, better you understand these fundamentals, you can also understand all the advanced stuff easily. So after the break, there will be a lot of fun stuff. Okay. When we discuss about floating rate instruments, you'll see all different kinds of magic. Okay. Right. Any question before we take a break? Everything clear so far? Okay. All right. Let's take a 5 minutes break and we'll continue. All right. So let's moving on. We talked about fixed coupon bonds. Now let's talk about floating rate notes. Quick audio check. You guys can hear me? Okay. Floating rate notes. So this is interesting. Very, very interesting. A floating rate note gives you floating coupons. What does floating coupon mean basically is in advance, you don't know what the coupon amount will be. That's the most interesting part. You will only get to know when you reach the reset date. Okay. When you reach the um, start date of the period for that rate, at that point the rate becomes available. Until then, it's random. Nobody knows what the coupon payment would be. Okay. So when you approach that the start point of the period, when you reach there, the rate becomes known and your coupon becomes determined or deterministic at that instance. So for example, if you look at this cash flow diagram, this is what I'll use for swaps also. It's the most generic parameterization of the instrument. So this is our observation date or valuation date. Okay. T alpha is your first reset date. T alpha is your first reset date. T alpha, so it goes on. T alpha plus 1, T alpha plus 2, T alpha plus 3, all these are different dates. In the middle, I have like I minus 1 and Ti, two dates. And the final date is T beta, that is the last reset date. Now, how do they work is your first coupon payment starts on T alpha plus 1. That's a floating coupon. At T, you have no idea what that coupon amount would be. Okay. Once you arrive here at T alpha, that's the first reset date, you see this rate that is available. It is no longer random, right? You can see it. Between T alpha to T alpha plus 1, you know the rate. Okay. So based on that rate, you get the coupon payment. So here is a more generic argument happening in between somewhere. So obviously at every time remember on T alpha, there is no payment. It's the first reset date. The payment starts from the next one. So let's say there is an intermediate 2 time points, Ti minus 1. You also have some coupon payment there, which would have been decided a period prior to this. But let's talk about Ti. So what will happen is the coupon payment that you will get at Ti would be decided at Ti minus 1. How much will that be is notional times the simply compounded floating rate. Simply compounded floating rate. Floating rate will become fixed because it is from Ti minus 1 to Ti. L Ti minus 1 to Ti, this notation is self-explanatory, is the rate applicable between Ti minus 1 to Ti, which becomes known when you arrive at Ti minus 1, which is a reset date, times the year fraction tau. Tau is the gap between these two. Okay, the length of the period for which the coupon payment is made. So every time you'll get something like this kind of a coupon payment. It's floating, but becomes known or when you reach to the reset date prior to that date. Okay. On T beta is the last reset date. You'd get some payment which would have been decided here based on the rate available. You'd get. So here the payment would be N floating rate between T beta minus 1 to T beta times tau. Also at the end, you get a notional. So it's similar to fixed rate bond. The only difference is the coupon floating payments are not known in advance. You just only when you get there, you know it, not before that. So this looks like a complicated instrument. How do we value it? The instrument looks complicated because a lot of random quantities are there. However, FRN or floating rate note, always the PV of that is always equal to notional on any reset date. Okay, and that is a very useful result. It's surprising. So what I'm saying is the value of a floating rate bond is equal to notional N. That's it. On specific dates. And those specific dates are reset dates. So the value here is N. The value here is n. The value on every reset date would be n. Okay. Question from Vashist. So if you, why the messages are coming to me directly? Hold on. Okay. Question is, if it's quarterly frequency coupon payment, then first payment comes in 6 months, because T alpha there is no payment. Depends. See, you can do this. You can structure your floating rate bond note to start payments after a long time also. So today is T. Maybe your first payment is not until 1 year, 1 quarter. So first coupon payment is here, and then it goes every quarter. Possible. It's kind of like a forward floating rate bond. It's possible. So T alpha here would be 1. Okay, as you correctly mentioned, 1 year, and this would be 1.25, where the payment gets decided. But it could start right away also. So T alpha can coincide with T. So it becomes like a spot floating rate note. In that case, the first payment would be known at T. So for example, floating rate bond today is here. So this is 0. I'm just forget about small t, okay? 0.25, 0.5, 0.75, 1. If your first floating payment is here, then you kind of know it. Getting into the floating rate bond, the first coupon payment is known because 0 is a reset date, and the first interest rate is visible to you, so it's defined. The first one is known; it's deterministic. Going forward, these guys are not known. Okay, so depends. When does your floating rate payment start? It can start right away, or it can start sometime in future. But the idea remains the same. Everything becomes known only one period before, not before that. Okay, so as I mentioned, right, floating rate note discounts to par on any reset date. Yes, that's the question. Why? What is the reason behind this? Let me explain, and I'll use geometry. Well, not geometry. Yeah, some geometry and some algebra to prove this. It's a beautiful result. So exactly that's the question. Why floater discounts to par on reset date? So to understand this, consider a floating rate payment, just a single one floating rate payment. So you're standing here, Ti minus 1. That's a reset date. Reset date. Reset date means that this rate becomes known. This rate, which is L Ti minus 1 to Ti, the rate between Ti minus 1 to Ti, that becomes known on the reset date. So your floating payment that you are supposed to receive at Ti is given by this notional times rate times year fraction, tau. Tau is the distance between these two guys. Okay. Now this is known. So what I'm gonna do is I added a n as an inflow and also as an outflow. I can do that. That doesn't change the instrument, right? If I'm adding something and subtracting something at the same time, plus n minus n, doesn't change anything. All right. Now look at this. If you're standing here on that day, you're seeing this rate L Ti minus 1 to Ti. This would be your spot rate. This would be your spot rate standing at Ti minus 1, which is applicable for a maturity tau. Agree? That's known. Other things are not known, but this much I know. The spot rate for the time to maturity tau standing on this state is LTI minus 1 to Ti. And the same one goes in the coupon payment. Okay. Now look at the inflow. The inflow is this N plus N L Ti minus 1 to Ti tau. This is my inflow. Okay. L is a simply compounded spot rate. It is not continuous. Because remember, in the interest coupon payments, it is always simply compounded. We never use continuous compounding when calculating coupon rates. They're always simply compounded. So L is a simply compounded rate based on which you get the coupon. If L is the simply compounded rate, how do I value this cash flow at ti minus 1. Agree? That is how you discount, right? Bringing the value back to ti minus 1. Present value of the inflow. I have artificially added a n here. I'll show you why. Added and also subtracted, so that doesn't make a difference. Discounting the cash flow, the two cash flows, to ti minus, whoops, sorry, ti minus 1. So this is the discounting function that I'll use. How much is this? This is n. So the inflow which is happening at ti is equal to n at ti minus 1. So I just replaced this guy with n, but one time step before. Are you with me so far? It's magical because see, the numerator is dynamic based on the rate. Discounting is also dynamic based on the rate applicable, but they are equal to each other. So when you discount n plus coupon by the rate that becomes known, it is exactly n. Okay, at ti minus 1, it is exactly n. And this guy is still there. Okay. All right. So a coupon, right. So any floating payment that you initially we had only one floating payment. This is just a coupon payment. There is no notional here. Please remember, just a coupon payment, floating coupon payment that can be seen as inflow n at the beginning of the period, outflow n at the end of the period. Always remember this is a powerful machine. Okay, to look at floating coupon payments. Any floating coupon payment can be seen as notional inflow at the beginning of the period and a notional outflow at the end of the period. How simple this is. NN. Okay. Now, in case this was just a single floating coupon bond, so one coupon payment and one notional. So I would add an N here. There will also be N here, right? So if that N, additional N already exists, it will come here. Remember, a bond pays notional also at maturity. So you'll get an N here. These two N will get cancelled. So it will only boil down to this. Sorry. And that is nothing but notional at the beginning of the period. So floating bond discounts to par. Okay, let's do a full treatment. I don't want to confuse you with the second argument. Please, just for now, just remember that a simple floating coupon payment can be seen as a notional inflow and an outflow, like this. If I had this floating coupon outflow, okay, how would I do this? This will be n here and n here. Just the opposite. Okay. So I hope you're comfortable with this. Any floating coupon payment can be shown as two notional inflows and outflows. All right. Now let's use this idea to see why the floating rate bond discounts to par. So, okay. So we had this original floating rate bond, right? Floating payment starting from T alpha plus 1 every single time until T beta. And there is also a notional payment at the end because it's a bond. Now, this guy, I can write as this and this. Okay. The next one also, I can write as this, and there will be a n here. So basically you can feel that every point will have a positive n and a negative n. Okay. Ti at this point, this particular floating payment is this and this. Hope that makes sense. So you will have this plus n minus n at every single point. Look at the last one. In the last one, what will happen? This floating payment is seen as n here and n here. And before this, there would be n here also for the one before this, and it will have its own n there. Every point will have like this. At t beta, we have this and this, these two. But also at t beta, since you're getting the principal, so this is also there. So now if you see at every single point, net cash flow is zero. Zero, 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 everywhere zero. The only point it is not non-zero is here. So the whole thing reduces to a very simple diagram, this one. Okay. And you're standing here. The first reset date is T alpha. The entire floater discounts to N, or the present value is N at the first reset date. Any questions? I would recommend you to try this yourself once. Draw the cash flow diagram, use the argument that a floating rate payment can be um, decomposed into two notional payments, one inflow, one outflow, and just draw it out and see that everything cancels and you get this. Question from Yusuf. So there is nothing random. There are, see, coupon payments are random. What are the coupon payments you'll get are random, but the discounting that will be done, right? That is also kind of random. So present value, in present value terms, it becomes deterministic. This is very interesting. Okay. Yeah. So, but that's great. I mean, it's easy for us. We don't have to worry about stochastic valuation. It's just notional at the next reset date. Now, here is a caveat. So, how do you value it when you are in between two reset dates? There is a question. What would be the valuation on a non? That is exactly what we are going to talk about right now. Another question, does that mean that the floating leg PV of an IRS is the notional? That is exactly accurate. That is what we'll talk about next also. So the two questions that you asked is something that we'll discuss next. So next thing is, so we know that the value of a floater, remember when we say floater, it includes a principal or face value payment at maturity. So that whole thing can be seen as just a notional on the next reset date. Okay. So what if some time has passed and then there are some floating payments have been made and you are in between two reset dates. So this was the previous reset date. You received a floating payment. This is the new reset date. Okay. But when you are here, tell me something. The floating payment that you'll receive at this time point, is it known or unknown? When you are between Ti minus 1 and Ti, the floating payment that you'll receive at Ti, is it already known or unknown? It's known, right? It is known since this point, because the rate is from Ti minus 1 to Ti, which becomes known immediately when you land on Ti minus 1. So this is known. So I will treat this as a standalone fixed coupon payment. So just forget about this. This is just a simple cash flow that is deterministic. It's there. It is known. To value this standalone coupon payment, I'll just need to discount it here. That's all. What about the rest of the payments? So this is a separate treatment, okay? I know that if at this point, which is a reset date, from here to here, this entire thing will be converted to N. Look at this picture. This remains at Ti. Everything else beyond Ti, starting from this, so this cash flow all the way, all of this entire whole infrastructure discounts to N at this point, at Ti. Okay, that's it. So how do you value this? It's just too simple. I had the formula here. I don't know, maybe I didn't say. Um, Value is n plus n l ti minus 1 ti tau, and discounted by the discounting factor applicable between these two periods. So, I mean, we can do simple or compound, whatever rate you have available. So if you have, let's say, continuous compounded rate available, then you can do this, right? Or if you have simple compounding available, and you can go back and forth, no harm. Uh, so this tau is, okay, remember tau is between all the different ti minus 1 to ti. So this is kind of fixed. But here it will be year fraction between t and ti. That's the discounting factor. Use this or this, depending on if you have access to this or access to this. So that's the value. Is it clear, guys? Never be scared of floating rate payment ever again. It's so simple. Cool. Let's proceed then. Next instrument, forward rate agreement, which is used to be very popular. I kind of feel like it's a little injustice in the sense that when you read books today, they don't talk about the recent changes that have happened with regards to SOFR and how the instruments have evolved, which are now benchmarking the new risk-free rate so far. FRA is an instrument that is becoming extinct. Actually, it's not popular anymore. So I will probably be a new series just on this, how the instruments have evolved, IRS and everything, based on SOFR. Yeah, but for now we'll pretend that nothing has happened. Because, okay, so these instruments, FRA and IRS, they are the two instruments remaining that we'll cover, are very fundamental. Okay, so the ideas, the valuation ideas are important. Okay. Oh, there is another question. Good question. I did not want to discuss sensitivities duration here, but since you asked, the duration of floating rate note is reset period. That is correct. It is only the time till the next reset date, because see, any floating rate bond, oops, sorry, any floating rate bond discounts to par at n. Okay. So if you are here, and this is T alpha, the first reset date, this whole floating rate bond is just like a zero coupon bond with a notional n. There is nothing in between. So the maturity of the zero coupon bond is T alpha minus T. So basically, it's the time till the next reset date. That's the maturity time to maturity, and that's the duration. Remember, for a zero coupon bond, the duration is same as time to maturity. There is nothing in between. There is no coupon in between. Okay, so it will be the time to the next maturity. That's the same case here also, actually. So this cash flow plus this cash flow together, you are getting at TI, you're standing at T. So your duration for a floating rate bond essentially is just TI minus T. Time till the next reset date. That's all. So that's why floating rate bonds okay, interview question. Which is riskier? Fixed rate bonds or floating rate bonds? Riskier means potential to lose value, right? Which type of bond would be riskier? Indirectly, which bond has higher duration? Fixed rate bond. Fixed rate bond has potential to lose more value because of high duration. Floating rate bond adjusts automatically to the interest rate fluctuations. So that's why it is very less rate sensitive. Okay, good stuff. Forward rate agreement. Forward rate agreement. The idea of forward rate agreement is um, it's very simple. You are betting on a rate that is happening in future, T1 to T2. There is a rate between T1 and T2. We don't know that yet. We can only calculate the forward rate between T1 and T2. Standing at time T. So this is the valuation rate, small time T. Okay. There is a rate between T1 and T2, which is in future. One guy tells you that I will give you a fixed rate, K. There is some notional, N times K times period applicable is tau. So I will give you a fixed rate K. Okay. So naturally the interest payment that you'll get over the period is N times K times tau. You give me a floating rate, which we will know when we arrive here. When you get to here, you will see this rate L T1 to T2, and the floating coupon will become L N times L times tau. L is not known. Until you get to T1, you don't know L. Okay, so this is the arrangement. And in this particular case, we call it a receive fixed, because you are receiving the fixed coupon. So fixed receiver. You can just say receiver also. When we say receiver or payer, it is always with respect to the fixed one. Who is getting the fixed one? Who is paying? Who is receiving the fixed one? If you just say this is a receiver, FRA, that is understood that you are receiving fixed. It's always with respect to fixed. Now, question is, how do we value this? So with the magic trick that I just taught you, right? It's a cakewalk, actually. There are two different ways I can derive the value. Let's do it. It'll be fun. So you don't know L. Okay, standing at T, you don't know L. That is a random quantity. As you move forward in time, well, okay, before that, you don't know L, but you have an expectation of L. Expectation of L. Now, we are getting into hardcore quant finance. Let's not do that. Standing at time small t, you have an expectation of the future floating rate or spot rate. And that expectation is nothing but, who can tell me? Any guess, intelligent guess? There is you have an expectation of this random floating rate that will prevail from T1 to T2. It is the forward rate, exactly. Forward rate as observed at time T between these two dates, T1, T2. Okay, it is the forward rate. There is also a measure associated. Anyways, let's not get into that. So expectation of L is forward rate. Okay. And we can use this to calculate the value. Remember the golden formula, the value of any derivative. The value of any derivative is given by this expected value of discounted payoff. This formula will be important when we deal with options, because there we need distributions and expectations and things like that. But this is a golden formula everywhere, all the time. Expected value of discounted payoff. Okay, so we need three quantities. We need payoff, we need discounting, and we need expectation. So what is payoff? Payoff is simply this, n tau times k minus L. That's the payoff. Because of this guy, the whole payoff is random. I don't know how much I'll get, because I don't know L until T1. At T1, the payoff becomes deterministic. Now what is the discounting? Discounting would be simply, this is discounting. Value of a zero coupon bond, which is maturing at T2, discounted till small t. Because I am valuing at small t, so I need to multiply this zero coupon bond. That will act as the discounting factor. Okay, remember this guy only pays $1, right? At maturity at T2, value is here. So between discount factor and this value of this zero coupon bond, there is a small difference actually. But right now it is not important. Consider them interchangeably. You can use, I mean, this will serve as a discounting factor. The value of a zero coupon bond paying $1 at time T2 valued at time small t will serve as the discounting factor between small t and capital T2. And that is what I need to multiply to the payoff. Okay. And then we need an expectation. So if you take expectation of this guy, the payoff, everything is constant. This is known, this is known, this is known. Only thing is this is not known. But the expectation of L, unanimously, everybody said is the forward rate. Putting everything together, right? The value of the forward rate agreement is n tau k minus replace L with the expectation times discounting. That's the formula for FRA, value of FRA. Clear? Now, if this is the formula, first and foremost, how do we decide K? K is the fixed rate, right? Somebody will tell you, okay, I'll give you fixed rate K for this period, and you give me the floating rate. Okay, they'll agree to this FRA contract, but in that contract, K would be decided at the inception. This is how much, this is the fixed rate I will pay. How do you arrive at K? Well, the idea is you figure out a K or you fix a K such that the value of FRA at inception is 0. At the in the beginning, why do you want to have a value of FRA? Somebody will have to pay that value. Why do you need to do that? Why not fix K such that initially it costs nothing to enter into an FRA? And then later when the floating rate evolves, see, when you move forward in time here, your expectation of L will change. Your new expectation will be F T dash T1, T2. Accordingly, the value will get updated. So whoever wins will, gain money. So at inception, the value is 0. If it is 0, then K is simply this. So K at time 0, so see, I replace small t with 0 because this is at inception, not any arbitrary t. At time t equal to 0, this is my strike price, K, that needs to be fixed. So K is nothing but at the inception, what is the forward rate between T1 and T2 at time 0? That's the K. Okay. And you know how to calculate the forward rate, right? Given the yield curve, you need two spot rates, R 0 to T1 and R 0 to T2. In between these two spot rates, you can calculate the forward rate using the formula that we developed. And that's K. However, do not forget, if you are using continuous compounding, you'll get the answer in continuous compounding. You need to have the simply compounded formula. Okay. See, in the numerator, when you are multiplying the rates, these are coupon payments, which always are in simple compounding. Do not use continuous compounding to calculate the coupon payments ever. Okay, that's wrong. All right, so that's how you fix K. That's number one. Number two is, there is another formula. I like this one better. Here, you don't have to worry about, oh, by the way, how does the valuation change when you proceed forward in time? Only this thing will get updated, and this thing will also get updated. Discounting will also change because T is moving. You get closer and closer, and the expectation of your forward to also get updated accordingly. Just input those values, you get the updated value of FRA as you move forward in time. Remember, the theme is dynamic valuation. So small t is changing, yield curve is evolving, so your expectation would forward rate will be evolving. Plug in all those values, you get the FRA values as an evolution of, like, what would be how would the FRA value evolve? You'll get that. The other formula that I have here is, there are no rates here. Okay, this FRA, I mean, you can kind of feel it, right? What ingredients do you need? FRA is something that is sandwiched between these two dates, T1 and T2, correct? So, can I not have a formula that is purely based on the zero coupon bond prices for those two maturities? The second formula only has two zero coupon bonds, no rates. Okay, here everything is kind of mixed up. In the second one, is just see two zero coupon bonds, T2 bond and T1 bond. And there you have it. Okay. Do you want to know how this is derived? The first one you understood, right? Expected discounted payoff. The second one is actually just two steps. If you want me to do it, I'll do it, or else we'll skip it. Uh, 1 second. Sorry, give me one moment. Okay, we have this formula. And since you asked, I will derive it using two steps. What is the cash flow diagram? So we have NK toe here. Let's move this guy a little bit. Sorry. This is a floating rate. NL between T1 and T2 tau. This is equal to this stuff is equal to what? Oh, I think I did it opposite. Hold on. Let's think. Outflow would mean a bigger outflow. So this is how you need to remember between inflow and outflow. So see, if you have a floating rate inflow, okay, this is equal to, since this needs to have a positive PV, right? Because you're getting something. So you'll get N earlier and lose N later. This will ensure I have a positive PV because this is nearer, this is further. So overall is positive valuation, correct? If it is inflow, it needs to be this. If it's an outflow, in net PV terms, it should need to be negative. So you'll lose N earlier and get N later. Did that make sense? A floating rate outflow needs to look like this, plus and minus. Did you understand this, or you want me to explain again? Let me explain again. So see, if you have a floating inflow, okay, this is this is one reset date T1, this is T2. This is equivalent to, first you think logically, what is the present value of my cash flow? Is it positive or negative? I'm getting something, right? I'm not losing anything. So overall, whatever cash flow diagram you create, it needs to be, um, it needs to give me a positive present value. So I need to have an inflow earlier and outflow later, because if you this will have a lesser discounting, right? So getting money earlier and losing the same amount later will give you positive PV or no? Tell me. Correct. So this is the correct procedure. So this is how you remember. Okay, a floating inflow. Obviously, you will break it down into one inflow and outflow of the notional. But which happens earlier? How do you know? In net, is it an inflow? If it is inflow, the net present value needs to be positive. To have the positive present value, inflow N needs to happen earlier than the outflow N. Okay. The opposite idea applies to a floating payment outflow. The net present value of this guy must be negative. That means your outflow of N needs to happen earlier so that you lose more and you gain less in PV terms. Okay. So this is the correct decomposition. And this is equal to what? Look at this guy. These are now all fixed. N discounted to today. Uh, this is negative because an outflow, and inflow is N plus NK tau discounted to today. Is this the same? Check it out. So you can take N common. It will be 1 plus K tau discounted by PTT2 and minus PTT1 whole into N. Isn't this elegant? See, the first step that you do in interest rate world is you have the yield curve. Okay, first extract the spot rates from the liquid prices. Do an interpolation scheme, have a smooth yield curve. Okay. Next, find out the zero coupon bond prices. They don't have to exist or being traded. You need to find out all this PTTI, assembly of zero coupon bond prices, because these will be used left, right, and center in all of the derivative pricing. So you need to have the discount factors handy with you. Once you already have this, right, pricing FRA is cakewalk. You just need to cherry pick two discounting factors from the list, plug it in, and then you have the valuation. Okay. Now let's move on to IRS. I wanted to cover all the Excel workings today, but looks like we're up on time already. It might be too much. We'll figure out another way to go through the Excel examples. Okay. Yeah. Let's proceed. I'm taking time on this because it's very, very foundational. The better grasp you have on these fundamental topics, right, it'll be easier for you. Yeah, I'll need 1 hour dedicated session for the Excel walkthrough. Maybe we can schedule it on some weekday if it works. So we can discuss on the chat. So the last instrument for today is IRS. Okay, interest rate swap. Now, plain vanilla interest rate swap involves fixed rate payments versus floating rate payments, and we already know how to work on with these ones today, right? We know how to treat fixed rate payments and floating rate payments from a valuation perspective. So this is called as a fixed floating IRS, but you can have different types of IRS. You can have floating IRS. So there'll be two rate curves. There'll be some basis between them, and then you exchange floating based on one yield curve, and the other guy gives you floating based on the other yield curve. That also is there. All right. So how can you value IRS? Using FRA method. Essentially, if you look at IRS, it's just a series of FRAs, and we know how to value the FRAs. So you just have to do multiple valuations of different FRAs, add them together, then you have the value for IRS. Or we can use the bond method. Now, bond method, first let's look at the cash flow diagram, it will be clear. So if you look at IRS, right, this is the receive fixed IRS. First reset date T alpha, next reset date T alpha plus 1, the same stuff goes on, right? So I am receiving fixed coupon payments. NK tau, K is the fixed rate. Okay, receive fixed. Please remember, there is no exchange of notional at the end. It is only the coupon payments. IRS does not have any notional. Okay, but some of the FX cross-currency swaps have notional exchange as well. But here in just plain vanilla IRS, we don't have exchange of notional. So at the end, you don't see a N at the end. Okay, so inflow is fixed, and then we have floating outflows for a receive fixed swap. All right, or you can just say receiver swap. It's the same thing. You're receiving fixed. From a valuation perspective, we want to value the IRS here at time t. This is easy peasy, right? I mean, we already know how to do it. So there are two ways to look at it. One is, you see, these are series of FRAs. Look at this part. This is one FRA. Forget about all the other items in this entire diagram. Just have focus on this one and this one. So this is just a value of FRA. Okay. The rate is between T alpha to T alpha plus 1. Remember, this was T1 and this was T2, correct? And what else? That's it. So value at time T, you can calculate the value of this FRA. Next, look at the next one. So this is another FRA. The rate applies between, or let me focus on this one, then this one. So the rate is between Ti minus 1 to Ti. So now this is T1, this is T2, and valuation date is here. So you just need the corresponding zero coupon bond values, right? Discounting factors, and then put it in the equation. You'll do not calculate forward rates. That is boring. Right? So use the second formula, is what I'm saying. You know all of these for different maturities. Just plug it in and find out the values of the individual FRAs, add them. You're done. Okay. So series of FRAs. The second method is bond method. So in bond method, what we do is you can think of this as a long in fixed rate bond and short in floating rate bond. However, there is something missing. If you look at the inflows, does it qualify to be a bond, fixed rate bond, or do you need something? Look at the inflows and look at the outflows. Are they ready to be called as bonds? Yes, there are a series of payments. But is it a bond yet? Or do we need something? Notional payment, exactly. At the end, we need a principal payment that is missing. But that's okay because if it is missing on both sides, I can add it on both sides. Doesn't change anything. I'll add and remove. It's fine, right? So now if I do that, then the inflow becomes, the entire inflow cash flow stream becomes a fixed rate bond. And the outflow is a floating rate bond, which we know how to value now. So bond method is, it gives you a shortcut. Okay. And you can pretty much see, I have done the diagram here. So the fixed coupon starts from T alpha plus 1, fixed NK tau everywhere. And in the end, it is NK tau plus N. I added this artificially. And the entire floating rate bond discounts to par at the first reset date. Correct? Uh, the one thing remember, so this is a common mistake. Do not create the N here. That'll be wrong. It is always one reset date before the first floating payment. Okay. So that is something to keep in mind. And having done this transformation, there is nothing stopping you to value this. It's so easy. So look at this. Coupon payments, NK tau, starting from I equal to alpha plus 1, this guy, all the way till this guy, beta, correct? Discounted by the respective zero coupon bonds. Valuation date is fixed at T. Only the maturities is TI, which is the first one will be T alpha plus 1, second one will be T alpha plus 2, all the way till T beta, right? So you already would have calculated the zero coupon bond prices for different maturities. Just plug in discounting factors. You get this. And additionally, there is a N inflow at T beta, that is this guy, and N outflow at T alpha, that is this guy. That's the valuation of IRS. Simple stuff. Okay. Yeah, it becomes complicated a little bit when you are in between two reset dates. So suppose you are valuing here. Fixed rate ones are still okay, right? You just need to adjust the discounting factors. The amounts are same. But for floating one, you have to do that other trick. Okay. So the whole thing will discount to par here, N. Plus there would be a floating coupon payment would have been decided at this point. So n something L, let's say T alpha to T alpha plus 1 times tau. This coupon payment would additionally be there. On top of that, all the remaining floating payments would discount to n. Take these two together and adjust your formula. That's how you do it. All right. Okay. Let's see. Yeah, 5 more minutes. There is a concept called as swap rate. Okay. I write swap rate. This is not my notation. In most of the very good interest rate derivative books, you'll find this notation. Swap rate S parameterized by alpha beta. What is the alpha beta? Alpha beta tells you what is the tenor of the swap, right? Alpha and beta are the first and last reset dates. So the swap rate involving an IRS that spans from T alpha to T beta. Remember, T alpha is the first reset date. You don't get any payments on that. You get it after one period. Defined at any time T, because you're depending on your valuation date. IRS contract remains the same, but your T moves forward. Okay. So starting with, so here is another important detail. If your T is here, T alpha is here, right? This is called a forward swap. Because your payments start, you can think of this like this. The first reset date is in future. Payment will start here, floating, fixed, whatever, forward swap. And just a swap, vanilla swap, is when these two dates coincide. Same discussion we had in floating rate mode, right? T equal to T alpha. So the first, so this is T alpha plus 1, and here T equal to T alpha. So if you're here, inception of IRS, the first payment, floating payment is known. This is known, and then it continues. Okay. So this is just the swap. This is a forward swap. Okay. As we move in time, T evolves, everything evolves, right? Valuation evolves, everything evolves. The swap rate also evolves with time T. Contract remains the same cash flow structure, everything. Maybe if you move too much forward, there will be some payments that would have already happened. The maturity of the IRS will reduce, but the schedule of cash flows remains the same. It's the same IRS contract, but as you move forward in time, the swap rate also evolves. Now let's understand what is swap rate. Swap rate, very simple definition. Swap rate basically means it is the fixed rate in the fixed bond. So we have two bonds, right? Fixed bond and the floating bond. It is the fixed rate in the fixed bond that makes the value of the swap zero. Fixed rate of the fixed bond that makes the value of the IRS zero. So basically, if you look on the bottom, we have a floating rate bond. Okay. There would be some equivalent fixed rate which will make the value of the fixed rate bond equal to the value of the floating rate bond, so that plus minus will get cancelled, your valuation would be zero. At every single point, whatever floating rate bond structure you have, there would exist an equivalent fixed rate such that the valuation is zero at every single point. That's the swap rate. Swap rate is the fixed rate of the fixed bond, or you can fixed, everybody understands the fixed rate of the fixed bond, right? Swap rate is the fixed rate that makes IRS value zero. That's the definition you need to remember. Okay, so if it makes it zero, right, then what makes it zero? So let's keep, instead of, let's do this. At any point, right, the value of IRS is given as n tau. I'm taking S instead of K. See, K is something that is fixed at inception. You cannot change that. I'm saying it is the hypothetical fixed rate coupon, right? So let's say that is S. I'll write this. This is the fixed rate, some hypothetical fixed rate at time t, okay, valuation date, such that pt beta minus nptt alpha, this valuation is 0, for which, let me use a different color so that uh, what is this fixed rate such that this is 0? You can solve it. Everything else is known. At every single valuation time point t, you can solve this guy. That makes this equation 0. That's the swap rate. Now, at time t equal to 0, special case, at time t equal to 0, I decided on a fixed rate, k. And I decide the k is such a way that the value of the swap is 0. So basically, S alpha beta at time 0, the swap rate at time 0 is what gets fixed. Okay, so let's solve this equation. S alpha beta t is equal to n gets cancelled. Actually, you don't need n. P alpha minus t beta divided by tau sum of I equal to alpha plus 1 to beta. This is the formula, ready-made formula for swap rate at any point in time. Okay, now you might think this is looks complicated. It's not complicated. To remember this is very easy. Look at the first one. This is the discounting factor till the first reset date. Okay, discounting factor for the last reset date divided by tau is the year fraction settlement frequency, right? If it's quarterly settlement, it will be 0.25. If it's semi-annual, it will be 0.5. Sum of discounting factors. Please remember, do not include the first one. In the bottom, it goes from alpha. So if I look at the diagram is messed up. Okay. Uh, T alpha, T beta. Okay. This you understood? This is this discounting factor any day. The last one is this discounting factor divided by tau, sum of discounting factors that starts from T alpha plus 1, guys. Please remember from here, this plus this plus this plus this plus this. From actual cash flow, exactly. Correct, because it is coming from this expression where you are discounting the fixed cash flows. Fixed cash flows start from the next period, not from T alpha. Okay, but this T alpha is coming because we discounted the floater to par, but it goes to the previous reset date, even before the first cash flow. That's why this one is separate. Okay, so that's the formula. That's it. At time t0, what happens? Put t equal to 0. P0 T alpha, whatever this is, everywhere 0. So you might be thinking, sir, this formula differs from what we have learned in books a little bit. I'll explain why. The formula that we derived is for a forward swap. Forward swap is a more general entity than the plain vanilla swap because your cash flow can start in future at some point. Doesn't have to start right away. If your swap is such that the first coupon payment is right away, that means T is equal to T alpha. Remember? So you are standing here, inception 0. Okay. And this is T alpha plus 1 because 0 equal to T alpha, for example. So your payment starts right away. This is known. In that case, you put T equal to T alpha, probably you will have something familiar. 0, 0, 0, 0 minus 0 T beta divided by tau. Actually, let me not rewrite a whole lot of stuff. Can you tell me what is P00, guys? What is PTT in general? Zero coupon bond maturing at T, valued at T. It is 1. Exactly. There is no discounting. It is 1. So P00 would be 1. And this is something probably you would have seen. So how do you calculate swap rate in the inception? This is for a plain vanilla swap when it starts right away. Sum of alpha, sorry, I equal to this 1 is the discounting factor because it starts right away. Okay. So 1 minus last discounting factor divided by tau times sum of all the discounting factors. This naturally will not include the 1. Will never include the 1. It will start from the next one. So this is the swap rate, and you can calculate it at any point in time, not just at inception. Whatever is the swap rate at inception, that gets fixed as the fixed cash flow because this will ensure that the IRS value is 0 at the beginning. Okay. The last aspect of this is you can use, so remember how we, for valuation of FRA, we can use the updated forward rate, keep updating the forward rate and you get the value of FRA. For IRS also, if you can plug in the updated swap rate, you can value the IRS. So this is one alternative way to value the IRS. Understand this. You are supposed to get K all your life, correct? That got fixed in inception. Nobody can change it. NK tau, fixed payments you're going to get received. The floating payments are all random. We don't know. But at any point in time, this floating rate bond can be replaced by a fixed rate bond with the fixed coupon rate being swap rate, because the definition of swap rate is such that it equates the fixed bond and the floating bond. So can I look at this entire floating rate bond as a hypothetical fixed rate bond having fixed rate is equal to this? Because this makes them equal. S alpha beta t is the equivalent fixed rate of a fixed rate bond, which equals in value to the floating rate bond. So instead of looking at the floating rate bond as a floating rate bond, I can look at it as a fixed rate bond with a hypothetical fixed rate which is equal to the swap rate at that time. So I'm getting K fixed from the inception, and I'm paying a hypothetical fixed, which is the swap rate, because that matches the floating bond outflow. So it's just fixed minus fixed. And this guy keeps getting updated with T. This is an alternative value. So it's just now difference of the two cash flows, N tau receive fixed minus pay hypothetical fixed. Okay, that's the swap rate times all the discounting factors. So all these cash flows are happening, right? From T alpha plus 1 onwards, discount everything back to T. Alternative formula. Question from Riddle: what happens when fixed and floating flows are in different frequency? Oh, that's a great question. Then I cannot use this formula in this fashion, but I can use them separately. So the discounting factors will not be overlapping, but you can still do it. I mean, fixed, this is a fixed bond, and say we have a floating bond here happening at a semi-annual frequency. Okay, still you can calculate a equivalent swap rate for the floating rate bond and use that, only that the discounting factors will not be the same between top and bottom. So it'll be different discounting factors. Okay, if it doesn't work out, then go back to the older formula, this one. Here also it'll be you have to treat them separately. The discounting factors will not be common because the cash flow what vertices will not be matching. So just treat them as two different fixed floating, and you can do it. Is that all I had? Yes. Okay, cool. I did have end-to-end example for Excel. I don't think right now is the right time to do that. It'll take at least an hour. So I'll schedule another follow-up sooner than later so that we still remember theory. I'll share this notes with you and we'll go from there. Okay, any questions before we wrap up? All right then. Hope you enjoyed this session. I'll see you soon. Bye, guys.